Hello, in this lecture we'll find out the area of the green shape. In the drawing we have a circle. Inside this circle we have peripheral angle ACB. This is peripheral angle ACB that equals to 70 degrees in its size. And we also know that the radius of this circle R equals to 2. And we also have in this drawing this common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. Tangent PA is tangent to this circle at point A, and tangent PB is tangent to this circle at point B. And then, again, our mission is to find out the area of this green shape. So first of all, we join points O and B together by a straight line. Point O is of course the center of the circle. We join points O and B by a straight line. So, point O is the center of the circle. Point B is the point of the circle itself. Therefore, OB is the radius of this circle. That is equal to 2. Here we'll implement rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing you have a circle, and we also have here tangent AB, that is tangent to this circle here at point M. Point M is the point of tendency of tangent AB with this circle. And the radius OM that is equal to R is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees. Actually, we can implement rule 1 in our drawing. Why? Because in our drawing we have the radius OB that is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius OB. If PB is perpendicular to BO, it means that this angle equals to 90 degrees. Is the right angle. Likewise, according to the same rule, rule 1, here the radius OA that is drawn to point A, that is the point of tendency of tangent PA with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PA will be perpendicular to the radius AO. If PA is perpendicular to AO, it means that this angle equals to 90 degrees. According to the same rule, rule 1. In the next step, I will present to you a new rule, and we'll implement the new rule in our drawing. The new rule is rule 13. According to rule 13, a central angle is twice as large as the peripheral angle subtended on the same arc. So in the drawing we have a circle. Inside this circle we have peripheral angle ACB. This is peripheral angle ACB that is actually subtended on chord AB. In addition, we have the central angle AOB. This is the central angle AOB that is subtended on the same arc AB. So according to rule 13, this rule the center angle AOB will be twice as large as the peripheral angle ACB that is subtended on the same arc AB. And we know that the size of peripheral angle ACB is theta, therefore the size of the center angle AOB will be equal to 2 theta. Okay? So we can actually implement rule 13 in our drawing. Why? Because in our drawing we have the peripheral angle ACB. This peripheral angle ACB is subtended on arc AB and it is equal to 70 degrees in its size. Therefore, the center angle AOB, this is the center angle AOB that is subtended on the same arc AB. And therefore, according to rule 13, the size of the center angle will be twice as large as the size of peripheral angle ACB that is subtended on the same arc AB. So the size of the peripheral angle ACB is 70 degrees. Therefore, the size of peripheral angle AOB will be equal to 70 degrees times 2, that is 140 degrees. So in conclusion, found out that according to rule 13, this center angle will be equal to 140 degrees in its size, twice as large as the peripheral angle ACB that is subtended on the same arc AB. In the next step, we join points P and O together by a straight line. By joining points P and O, we created here two right angles, the right angle POA and the right angle PBO. So in the next step, we'll prove that those two right angles can go into each other. So write it down. We'll prove that the right angle POA is congruent to the right angle POB. So why those two right angles can go into each other? First of all, side AO of the right angle POA is equals to side BO of the right angle PBO. They are both the radii of the circle, therefore they are equal to each other. AO equals to BO equals to 2. Read again. AO equals to BO equals to 2. In addition, this is side PO, that is the common side, it belongs to both triangles. So we can write down that PO equals to itself is a common side, it belongs to both triangles. Repeat again. PO equals to PO, it's a common side that belongs to both triangles. And finally, side PA of the right triangle POA equals to side PB of the right triangle PBO. PA equals to PB according to rule 2. Repeat again. PA equals to PB according to rule 2. I will remind you quickly what is rule 2. according to rule 2, the lengths of two tangents from a common external point to a circle are equal. So in the drawing we have a circle and also the common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule, rule 2, they are equal to each other. That is to say, PA equals to PB. So I can actually implement rule 2 in our drawing. Because in our drawing, from the common external point, point P, we have two tangents to the circle, tangent PA and tangent PB, and according to rule 2, they are equal to each other. That is to say, PA equals to PB according to rule 2. So I actually proved that all the three sides of the right triangle P or A are correspondingly equal to all the three sides of the right triangle, this right triangle P or B. Therefore, those two right triangles can go into each other according to side rule. So I write it down. The right triangle P or A is congruent. This is the sign of congruent to the right triangle P or B. According to side rule. And from the fact that those two right triangles can run to each other, we conclude that those two angles are equal to each other. So this is angle AOP, and this is equals to this angle. This is actually angle BOP. So those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore those two corresponding angles must be equal to each other. So if we define the size of this angle as alpha, then the other angle must be equal also to alpha because they are equal to each other. So if one of those two angles equals to alpha, then the other angle must be also equal to alpha. So this is angle alpha and this is angle alpha. And from the drawing it is very easy to see that alpha plus alpha equals to 140 degrees. In total, this angle A or B is equals to 140 degrees, therefore alpha plus alpha equals to 140 degrees. That is to say 2 alpha equals to 140 degrees. We divide this equation by 2, and finally we get that the missing angle alpha equals to 140 degrees over 2, that is 70 degrees. So, the missing angle here, alpha equals to 70 degrees in its size. And this is also angle alpha that equals to 70 degrees in its size. So, in the next step, I present to you a new notion that is a sector. What is a sector? A sector is a part of a circle Here we have a circle that the green shape AOB is a sector of this circle. Sector AOB consists of two legs. The first leg is AO and the second leg is BO. They are both the radii of this circle is equal to R, therefore they are equal to each other. And the angle between those two legs, AO and BO, is this angle, angle theta. So a sector is like a slice of pizza that consists of two legs and the arc AB, that is the arc between those two legs. Both those two legs are the radii of this circle, therefore they are equal to each other. And angle theta is the angle between those two legs, AO and BO. So what is the area of this sector, the green sector AOB? The area of the green sector AOB equals to the area of this circle that is actually pi r squared times the angle between the legs of this sector that is theta over 360 degrees. Repeat again, the area of this circle equals to pi r squared times theta over 360 degrees. Repeat again, our mission is to find out the area of this green shape. So, what is the area of the green shape? From the drawing, it is very easy to see that the area of this green shape is equal to the area of this right triangle AOP plus the area of this right triangle BOP minus the area of this sector, sector AOB. Repeat again, the area of this green shape equals to the area of the right triangle AOP plus the area of the right triangle BOP minus the area of sector AOB. Here the rounded line above AOB is the sign for a sector, it means sector AOB, and the square bracket is the sign for area, so this expression in total means that the area of sector AOB. Okay, repeat again, the area of this sector, the area of this green shape equals to the area of the right triangle POA plus the area of the right triangle POB minus the area of this sector to sector AOB. So in order to find out the area of this right triangle AOP, we have to find out the length of side AP. Side AP, it is actually the height to the base AO of this right triangle, triangle POA. So what is the length of AP? So in the right triangle POA, it is very easy to see that triangle 70 degrees equals to AP over AO. Repeat again, in the right triangle AOP, triangle 70 degrees equals to AP over AO. So it is equals to AP that is the missing side, over AO. AO is the radius of this circle, that is equal to 2. So we substitute AO by 2. In we found out that tangent 70 degrees equals to AP over 2. Tangent 70 degrees is 2.75, and it is equals to AP over 2. Here we multiply this equation by 2, and finally we get that the length of side AP of the right triangle AOP, it is equals to 2.75 times 2. 2.75 times 2 is 5.5. So we found out that AP equals to 5.5 units in its length. So the length of this side AP, is equals to 5.5 units. So here we have already found out that those two right triangles can go into each other. And because of the fact that they can go into each other, they also have the same areas. Okay. So the area of triangle AOP equals to the area of triangle BOP. So we can substitute the area of triangle BOP by the area of triangle AOP. You do it now and you get that the area of the green shape, in total it is equals to the area of the right triangle AOP plus the area of triangle BOP, and because of the fact that those two right triangles can go into each other, they have the same area, so we substitute the area of triangle AOP by the area of triangle AOP, because they have the same area. So this is the area of triangle AOP plus the area of triangle AOP again, minus the area of sector AOB. So actually found out that the area of the green shape is equals to the area of triangle AOP plus the area of triangle AOP, that is 2 times the area of triangle AOP, minus the area of sector AOB. Now we find out the area of triangle AOP. The area of triangle AOP is equals to the area of any triangle equals to the base of the triangle times the height to the base over 2. So we take the base of this right triangle AOP is AO, so it will be the base is AO times the height to the base is AP. Why? Because the AP creates 90 degrees with the base. So the height is AP over 2. The base AO equals to 2 times the height AP is equals to 5.5 over 2. So we found out that the area of triangle AOP equals to times 5.5 over 2. 2 over 2 is 1, so 2 will get cancelled, and we're left only with 5.5. In conclusion, we found out that the area of the right angle AOP is equal to 5.5 square units. So we have to multiply the area of the AOP by 2. So it will be 2 times 5.5, that is actually 11. In conclusion, found out that the total area of this right angle AOP plus this right angle BOP is equal to 11 square units. In the next step, we will find out the area of this sector AOB. So what is the area of sector AOB? The area of sector AOB equals to the area of the circle that contains the sector, that is actually pi r square, times the angle between the legs of the sector, that is 140 degrees. Here, this angle equals to 140 degrees over 360 degrees. So it is pi r square. R is 2, therefore r square is 2 squared, that is 4. So the area of the circle equals to 4 pi times 140 degrees over 360 degrees. In total, the value of this expression, 4 pi times 140 degrees over 360 degrees, it is equal to 4.88 square units. If we're going to find out that the area of sector AOB is equal to 4.88 square units. Repeat again, the area of the green shape is equal to the area of this right angle AOP plus the area of this right angle BOP, and we already found out that the sum of those two areas is 11 square units minus the area of this sector AOB, and we just write down found out that the area of sector AOB is 4.888 square units. So the area of the green shape equals to 11 minus 4.888 is actually 6.111 square units. So in conclusion, we found out that the area of the green shape in total it is equal to 6.111 square units. And that is the answer to the question. Repeat again. The area of this green shape equals to 6.111 square units. So in the next step, I will summarize the lecture. In this lecture, we found out the area of this green shape. And again, in this lecture we found out the area of this given shape. So in the drawing we have a circle. Inside this circle we have this peripheral angle ACB that is equal to 70 degrees in size. In addition, we know that the radius of this circle R equals to 2 units. And we also have the common external point, point P. From the common external point, point P, we have two tangents to this circle. Tangent PA, that is tangent to this circle here at point A, and tangent PB, that is tangent to this circle here at point B. Again, our mission is to find out the area of this fringe shape. So, first of all, we know that point O is the center of the circle, so we join points O and B together by a straight line. Point O is the center of the circle, point B is the point of the circle itself, so OB is the radius of the circle that is equal to 2 units in its length. So here we can implement rule 1. We have the radius OA that is drawn to point A, that is the point of tendency of tangent PA with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PA will be perpendicular to the radius AO. If P is perpendicular to AO, it means that this angle equals to 90 degrees. Likewise, we have the radius OB that is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to the same rule, rule 1. Okay, then I presented to you the new rule and implemented the new rule in our drawing. Actually, the new rule is rule number 13, and according to rule number 13, a central angle is twice as large as the peripheral angle that is subtended on the same arc. So here, according to rule 13, a central angle is twice as large as the peripheral angle subtended on the same arc. So, in the drawing we have a circle. Inside this circle we have the peripheral angle ACB. This is peripheral angle ACB. This is equal to theta. And this peripheral angle ACB is subtended on arc AB. And we also have the central angle AOB that is subtended on the same arc, arc AB. And therefore the central angle that is subtended on the same arc as the peripheral angle will be twice as large as the peripheral angle. And because of the fact that the peripheral angle equals to theta, therefore the central angle will be equal to 2 theta. Okay? We can actually implement all 13 in our drawing. Why? Because in our drawing we have peripheral angle ACB. This is peripheral angle ACB. This is equal to 70 degrees in its size. And we also have, and peripheral angle ACB is subtended on this arc, arc AB. And we also have the central angle AOB that is subtended on the same arc, arc AB. Therefore, according to rule 13, the central angle will be twice as large as the peripheral angle that is subtended on the same arc, arc AB. And because of the fact that the peripheral angle equals to 70 degrees, the central angle will be equal to 140 degrees. Okay? So, in the next step, we join points O and P together by a straight line. By joining points O and P, we get it here two right triangles, the right triangle AOP and the right triangle BOP. In the next step, we proved that those two right triangles can go into each other. So why those two right triangles can go into each other? First of all, side AO of the right triangle AOP is equal to side BO of the right triangle BOP. They're both the radii of this circle, therefore they're equal to each other. Repeat again, AO equals to BO equals to R, that is equal to 2. In addition, we have side PO, that is the common side that belongs to both triangles, so we can write down that side PO equals to itself as a common side that belongs to both triangles. Repeat again, here PO equals to PO as a common side that belongs to both triangles. And finally, side PA equals to side PB. Side PA of the right triangle AOP is equal to side PB of the right triangle POB. Those two sides are equal to each other according to rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. So we have here the common external point P. From the common external point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. Repeat again. PA of the right triangle AOP equals to side PB of the right triangle POV according to rule 2. So actually proves that all the three sides of this right triangle POB are correspondingly equal to all the three sides of this right triangle AOP. Therefore, those two right triangles can go into each other according to side rule. Repeat again. The right triangle POA is congruent. This is the sign of congruent to the right triangle POB according to side rule. And from the fact that those two right triangles can go into each other, we conclude that those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding angles, those two corresponding angles must be equal to each other. That is to say, angle AOP in the right triangle AOP equals to angle BOP in the right triangle BOP according to the rule that I mentioned. So, because of the fact that those two angles are equal to each other, it means that if this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. So if we define this angle as alpha, then this angle must be also equal to alpha, and therefore we get that alpha plus alpha equals to this angle, that is 140 degrees. Repeat again. Alpha plus alpha equals to 140 degrees. Alpha plus alpha is 2 alpha, so 2 alpha equals to 140 degrees. We divided this equation by 2, and finally found out that the missing angle alpha equals to 140 degrees over 2 is 70 degrees. So this is angle alpha that equals to 70 degrees in its size, and this is also angle alpha that is equals to 70 degrees in its size. In the next step, I presented to you actually the notion of a sector. What is a sector? A sector is part of a circle, as you can see here. The green shape AOB is a sector, and a sector is like a pizza slice. It consists of those two radii. The first leg of this sector is AO, and the second leg is BO. They are both the radii of the circle, therefore they are equal to each other. And the sector also consists of the arc AB that is between those two radii. This arc AB is between those two radii. And the angle between the legs of this sector, the leg AO and the leg BO, is this angle theta. So what is the area of this sector AOB? The area of this sector AOB equals to the area of the circle that is pi r square. times the angle between the legs of those two, this sector that is theta over 360 degrees. Repeat again, the area of the green sector AOB equals to pi r squared times theta over 360 degrees. Our mission is to find out the area of this green shape. What is the area of the green shape? From the domain, it is very easy to see that the area of this green shape equals to the area of the right triangle AOP plus the area of the right triangle BOP. The area of those two, the sum of the areas of those two right triangles. So, in total, the sum of the areas of those two right triangles will give us this area, the area of quadrilateral PBAO or AOBP minus the area of this sector AOB will give us exactly the area of this green shape. Again, the sum of the areas of those two right triangles will give us the area of this quadrilateral AOBP, and when we will subtract from the area of this quadrilateral APBO the area of this sector AOB, we'll get the area of this green shape. Repeat again, the area of the green shape in total equals to the area of the right triangle AOP plus the area of triangle POB. This will give us the area of this quadrilateral APBO, and when we will subtract the area from the area of quadrilateral APBO, the area of this sector ABO, we get exactly the area of this green shape. Okay, so the sum of the areas of the two right triangles will give us the area of quadrilateral APBO, and when we subtract from the area of quadrilateral APBO the area of sector AOB, we get exactly the area of this green shape. So in order to find out the area of triangle AOP, this triangle AOP, the right triangle AOP, we have to find out the area of this side AP. We know that this angle equals to 70 degrees and AOP is the right triangle. So in the right triangle AOP, it is very easy to see that triangle 70 degrees equals to AP over AO. Repeat again. In the right triangle AOP, triangle 70 degrees equals to AP over AO. AP is the missing side over AO. AO is the radius of this angle that is equal to 2. So we substitute AO by 2. So in conclusion, we found out that triangle 70 degrees equals to AP over 2. Triangle 70 degrees is 2.75. So 2.75 equals to AP over 2. We multiply this equation by 2 and finally found out that AP equals to 2.75 times 2. 2.75 times 2 is 5.5. So in conclusion, we found out that the length of side AP is 5.5 units. This side AP equals to 5.5 units. And we have to find out the area of this right triangle, triangle AOP. The area of the right triangle AOP equals to the base of the triangle, that is AO, times the height to the base, that is AP, over 2. Repeat again. The area of the right triangle AOP equals to the base times the height over 2, that is the area of any triangle. We choose the base, this is the base AO, times the height, that is AP, over 2. So the base is AO, the height is AP, divided by 2. So we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled, and we're left only with 5.5. In conclusion, we found out that the area of this right triangle AOP is equal to 5.5 square units. Okay. And now Repeat again. The area of this ring shape equals to the area of triangle APO plus the area of this right triangle BPO minus the area of this sector AOB. But because of the fact that we proved that the right triangle AOP, this right triangle AOP is congruent to this right triangle BOP, they also have the same areas. So we can substitute the area of this triangle BOP by the area of this triangle AOP because they have exactly the same areas. And therefore, we can write down in conclusion that the area of the ring shape equals to the area of triangle AOP plus the area of triangle AOP again, because we substitute the area of triangle BOP by the area of triangle AOP because they have the same areas. And we have to subtract from the sum of the areas of those two triangles the area of this sector AOB, minus the area of sector AOB. So the area of triangle AOP plus the area of triangle AOP is 2 times the area of triangle AOP, minus the area of sector AOB. We have already found out that the area of triangle AOP is 5.5, so 2 times the area of triangle AOP is 2 times 5.5. 2 times 5.5 is 11. So in conclusion, found out that the area of triangle AOP plus the area of triangle BOP, in total it is equal to 11 square units. Now we have to subtract from the area of those two right angles the area of this sector AOB. So what is the area of sector AOB? The area of this sector AOB. The area of any sector is equal to the area of the circle that contains the sector. In this case, this circle contains sector AOB, and the area of this circle is pi r squared, because r is the radius of the circle. So the area of the circle equals to pi r squared times the angle between the legs of this sector, that is 140 degrees over 360 degrees. So in total the area of sector AOB equals to pi r squared times 140 degrees over 360 degrees. R is 2, therefore r squared is 2 squared, that is 2. So in total the area of the circle is pi r squared, that is 4 pi times 140 degrees over 360 degrees. 4 pi times 140 degrees over 360 degrees, in total it is equal to 4.88. So in conclusion, found out that the area of this sector AOB is equal to 4.88 square units. Okay, because again the area of sector AOB equals to 4.888 square units. And we have already found out that the area of this ring shape, in total it is equal to the sum of the areas of those two right triangles minus the area of this sector. We have already found out that the sum of the areas of the two right triangles is 11 square units minus the area of sector AOB, that is 4.888 square units. It is exactly equal to the area of the ring shape, and 11 minus 4.888 is 6.111. So in conclusion, found out that the area of this ring shape is equal to 6.111 square units. Okay, thank you very much.